Hey everyone, my name is Spencer and I am representing my group for a final project presentation. For our project, we chose to analyze the UCS cargo plane from 2019. Each member chose to analyze different elements with various types of simulations performed. Since the bulkhead is the major support component of the fuselage, we ran sims on its most complex cross-section, shown on the right. The first load condition considers the bulkhead carrying the weight of a single payload. The second considers the event that during a crash, the payload will slam into the back face of the bulkhead. A drop test was performed to ensure integrity when dropped or when in transit. Instead of boundary conditions, setup of the drop test depended on height only, set to 4 feet. Under the two load conditions, condition 2 exhibited the largest amount of stress and displacement. Analysis shows that the majority of stress and displacement found in the upper section of the bulkhead, specifically on the thin truss-like structural elements. Proposed modifications in these areas improve results, with iteration 1 being more effective. No resonant frequencies within 3 Hz of the motor frequency were found. These images show the actual nodes of the project, the reduced nodes, the first iteration, and second iteration. Here are the two different boundary conditions. A 65 Newton load is applied to the top, side, and bottom of the stringer. This table represents the results of the original parts. This table here displays the results for the first iteration, and this table represents the second iteration results. The graph on the left shows the modal analysis that was done for the original part at 46 Hz. As for the graph to the right, it displays one study comparing all 3 parts after a simulation with huge improvement to the part. Although the plane contains both front and rear landing gear, the decision was made to focus on the rear as it was more complex. Considering how landing gear are loaded, the goal is to simulate buckling loads that the landing gear will experience if it were to free fall 2 feet upon landing. As can be seen, condition 1 exhibits the most stress and displacement, therefore iterations were based on this condition. From condition 1, the iterations were made at an attempt to reduce stress and displacement and to improve buckling loads. No resonant frequencies were close to the 46 Hz, which is good. For fatigue analysis of the landing gear, results were found based on 1000 cycles of condition 1. The blue dot is iteration 1's result, and the green is iteration 2's. Fortunately, both iterations exhibit excellent fatigue results. Both lie under their desired curve, the uppermost red line in the smooth section, so neither pose an issue to failing due to fatigue. On the top left is the image of the entire tail of both horizontal and vertical tail elements. The bottom left shows the reduced part being worked on. The top right is the first iteration, and the bottom right is the second iteration of a single part. 2 different boundary conditions were set, fixing the end where this will be attached to the tail boom, and holes where the screws will be. Another where rollers are in the opposing end, along with a load of 65 newtons on the top and front faces of the spar. These are the results for the different parts with each boundary condition and loads. The bottom right is the comparison chart when looking at boundary condition 1, with load condition 1 at 65 newtons showing heavy improvement of 50% or higher results from the original. Here are the results of the modal analysis of the original part. The motor arm experiences considerable vibration when in flight, and can translate this vibration to the rest of the aircraft. By optimizing the design of the support so that its resonant frequencies don't coincide with the frequencies of RC motors, users are able to interchange motors without having to worry about compromising the aircraft. The tests were conducted with supports being added around the motor arm, and the first 5 modal frequencies were analyzed. If any of the modal frequencies were below 250 Hz, then the test would be considered a fail. The final design had a minimum frequency of 256, which passes the preset criteria. Here's a table displaying the various frequencies of each iteration. My simulations focus on the wing spar of the cargo plane, and must withstand the stresses experienced during flight and while taxiing on the freeway. I wanted to simulate 3 conditions for which I think the wing will experience, as described above. The iterations I performed on the wing spar were primarily altering the cross-sectional area. I did my best to keep the iterations simple yet manufacturable. These tables report the stresses and displacements that each iteration experiences, with 3 different loading conditions previously described. None of the resonant frequencies of any design iteration come close to the frequency of the motor, which is desirable. This is the closed form solution I calculated for the aluminum wing spar under load condition 1. Thank you guys for watching.